Bismillahirrahmanirrahim. Assalamu alaikum. Dear viewers, I am Dr. Noshin Afshan and you are watching Dr. Noshin Afshan YouTube. I hope that all of you would be fine and I am thankful to you for watching this video. To watch more videos, please subscribe my channel and press bell icon. So our today's lecture is about molecular orbital diagram of oxygen and fluorine molecules. So now we start from the molecular orbital representation of oxygen molecule. Here the atomic number of oxygen is 8, that is 1s2, 2s2, 2px 1, 2py1 and 2pz2. Here this second electron can be placed in any of these three suborbitals because 2px, y and z, all these three suborbitals are at equal energy level. So now let's draw its molecular orbital diagram. Here the energy level increases from bottom to top, and here the atomic orbitals of one oxygen atom, and here the atomic orbitals of the other oxygen atom, because here it is O2, so one oxygen atom and the second oxygen atom. So starting from its 1s and 2s orbitals, here the same pattern would be followed as in the previous examples to form sigma 1s2, and it would be at the lowest energy level. We will start from the 1s here and here 1s. These would form the bonding molecular orbital, that is sigma 1s, and antibonding would be formed as sigma star 1s. Here there would be 2 electrons. Similarly in 2s, here it is 1s orbitals, and at higher energy level than this one it would be 2s. We will convert this one into 2s. 1s would be at the lowest energy level, then 2s, and the same pattern would be followed. Here it would be sigma 2s, then sigma steric 2s. So its energy level would increase as sigma 1s, then sigma star 1s, then sigma 2s. Here there are 2 electrons in all of these orbitals. Here sigma star 2s, and then after this one we see the case with these 3 p orbitals. The key difference between oxygen and nitrogen molecules lies here when these p suborbitals interact with each other to form the bonding molecular orbitals. Here these are the 2px, y and z. This is the 2px, this is 2py, and this is 2pz. Here the same pattern is followed here, 2px, 2py and 2pz. Now let's see that here 2px and y have been partially filled and 2pz is completely filled with 2 electrons. So it is 2pz that is completely filled, and other 2 are partially filled. Now the key difference is that 2px interacts with 2px of the other oxygen atom to form a bonding molecular orbital, that is sigma 2px, and it would be filled with 2 electrons. As you know that in nitrogen molecule 2py sigma 2p pi 2py and pi 2pz molecular orbitals were at the pi 2py and pi 2pz suborbitals were placed at the lower energy level as compared to this sigma 2px. But here in the case of oxygen molecule, the sigma 2px is at lower energy level as compared to this one, the pi 2py and pi 2pz. So this is pi 2py, this one, and this is pi 2pz. So now when we write down the alignment or the arrangement of these bonding and antibonding molecular orbitals, we place them like this. After this sigma star to s, we place this one, the sigma 2px. So here it is sigma 2px. It is also filled with 2 electrons, then pi 2py, that is at equal energy level as compared to the sigma 2pz. It is also filled with 2 electrons over here. Then there comes the anti-bonding molecular orbital, and after that it means the energy level is increasing in the next molecular orbitals. So similarly, here the sigma 2px is at the lowest energy level amongst these, and its antibonding molecular orbital would be at the maximum energy level. Here it would be sigma star 2px. It would be empty because these 2 electrons have been placed in sigma 2px. So it would be empty. And here 2py and 2py have these 2 electrons have also been placed in pi 2py. But you see that here the 2pz orbitals interact with each other to form a bonding molecular orbital with 2 electrons. The 2 electrons have been left over here. So these remaining 2 electrons would be placed in antibonding molecular orbital like this. The 2py would interact with 2py. It would be and here 2pz would interact with 2pz. In this case, as the experimental results indicate that the oxygen molecule shows paramagnetic behavior. It shows paramagnetic behavior. So the reason for this paramagnetic behavior lies here in the arrangement of these electrons. The 1 electron would be in pi star 2py and the 1 electron would be in pi star 2pz. Because of these 2 unpaired electrons, the oxygen molecule shows paramagnetic behavior. Then their arrangement with respect to energy level. After this pi 2pz, here comes the pi star 2py. It is also at the same energy level as pi star 2pz, but at the lower energy level as compared to sigma star 2px. So here it comes to an end. So with the help of these or this molecular orbital representation, we can find out its bond order. And its bond order, as you already know, that bond order is half of the difference between number of electrons in bonding molecular orbitals and number of electrons in antibonding molecular orbital. So 4 were in sigma 1s and sigma 2s. These were 4 electrons in bonding molecular orbitals, and here these 3 bonding molecular orbitals contain 6. So 4 and 6, total 10 electrons, and minus again sigma steric 1s and sigma steric 2s also contain 2 electrons. So these 4 and these 2, 6 electrons over here. So here it shows 4 by 2 is equal to 2. So its bond order is 2. That indicates that oxygen can form a double bond. So here its structure according to molecular orbital theory would be like this. Oxygen, one oxygen atom is doubly bonded with the other oxygen atom. So this was the case with oxygen. Now we move toward the fluorine molecule. What happens in the fluorine molecule? That resembles very much with the oxygen molecule, as the atomic number of fluorine is 9, that is 1s2, 2s2, 2px1, 2py2 and 2pz2. So the same case happens with 1s and 2s orbitals, that are sigma 1s2, then sigma star 1s2, then sigma 2s2, then sigma star 2s. Then it is at lower energy level as compared to the same case lies here. Here this is the atomic orbitals of fluorine, and here these are the atomic orbitals of the other fluorine atom. And here the 2py also contains 2 electrons that are here. And similar case happens with this 2py, it is also completely filled. Then after this sigma star, these bonding molecular orbitals remain the same. So after sigma star 2s, here comes the sigma 2px, filled with 2 electrons, and this is at lower energy level as compared to pi 2py. This is at equal energy level as compared with sigma 2pz, filled with 2 electrons, and this is at lower energy level as compared to this. Now here the 2 electrons have been left. These would be accommodated in these 2 antibonding molecular orbitals, and these 2 antibonding molecular orbitals would be completely filled. So in this way the number of electrons would be satisfied. So after this pi 2pz, here it comes the pi star 2py at the same energy level as compared to pi star 2pz, but at lower energy level as compared to sigma 2px, sigma star 2px. So here it comes to an end. I mean this their order with respect to energy level, and from this we can find out its bond order. That is, you can calculate that number of electrons in bonding molecular orbitals. Here 4 and total 10 electrons in bonding molecular orbital, and these 2 4 and these 4 electrons, total 8 divided by 2. So here it comes, that is 2 by 2, 1. So the bond order of fluorine molecule is 1. That shows that it forms only one bond. There is only one bond between 2 fluorine atoms. So our today's lecture comes to an end. So thank you very much for watching the video. Please subscribe my channel and press bell icon. Allah Hafiz.